Welcome to the first part of the lecture problems for Chapter 2. Let's begin with the first problem. Here, we're told that a car is moving along the x-axis, and we're asked to describe what the car is doing in each of the cases below. So let's begin with positive velocity, positive acceleration. Let's assume that the motion is occurring along the x-axis. Here we see that the car is moving in the positive I-hat direction, but because its acceleration is also in the positive I-hat direction, this car must be speeding up. In the next case, the car is moving in the positive I-hat direction, but because the acceleration is in the negative I-hat direction, the car must be slowing down. In other words, the car is still moving in the positive I-hat direction, but its velocity is being reduced every second since the acceleration is in the opposite direction. In the third case, the velocity is in the positive I-hat direction, but the acceleration is 0, so the car must be driving at constant velocity. In the next case, we have the car moving in the negative I-hat direction, which we might say due west, for example, if we wanted to use a different system of axis. And because its acceleration is also in the negative I-hat direction, it must be speeding up, just as in the first case, where both the velocity and acceleration were in the same direction. In the next case, the velocity is in the minus I-hat direction, but since the acceleration is in the positive I-hat direction and therefore opposite to the direction of motion, this car must be slowing down. Last, we have negative velocity, negative I-hat direction, and the acceleration 0, so once again we are moving at constant velocity. Okay, in this next problem, part A, we are told that a particle moves along the x-axis according to the equation 2t plus 3t squared minus t cubed. And x is, of course, in the SI unit meter. T is in the SI unit second. So we're asked to determine the particle's displacement and its average velocity for the time interval between t equals 2 seconds and t equals 3 seconds. Well, here, let's first determine the displacement of the particle. The displacement of the particle, by the way, this is the letter I, not I-hat. Sorry about that. Delta x is equal to x at the time period 3 seconds minus x at the time period 2 seconds. So this means that we have to make a substitution for t in the formula given to us for the position function of this particle. So we have x of 3 will be 2 times 3 minus 3 times 3 squared minus 3 cubed, because in fact 1 is the multiplier, minus 2 times 2 plus 3 times 2 squared minus 2 cubed. Here we expand this out, we get 6 minus 27 minus 27 minus 4 minus 12 plus 8. Actually, this should be a plus. In fact, that is an error. So let's be sure that we make that correction. That is plus, and therefore this will be plus 27. Okay, let's combine these numbers. 27 minus 27 is 0. 6 minus 4 minus 12 plus 8 is minus 2 meters. So the particle's displacement for this time interval is 2 meters, negative 2 meters. The average velocity in this time period is given by the displacement of the particle, delta x, what we just obtained, divided by the increment of time. Here, minus 2 meters divided by 3 seconds minus 2 seconds, which is of course 1 second, and so the average velocity is minus 2 meters per second. In the second part of the problem, oops, again, this is not a hat. Okay. In the second part of the problem, we need to determine instantaneous values for both the position and the velocity at t equals 3 seconds. Well, we know that x at 3 seconds will be 6 meters, because here these terms refer to x at 3 seconds. To obtain v at the instantaneous value of 3 seconds, we must first take a derivative of the position function and then substitute 3 seconds for t. So v of t is given by the derivative of x with respect to t, which gives us 2 plus 6t minus 3t squared. And then v at 3 seconds is 2 minus, sorry, this is 2 plus 6 of 3 minus 3 times 3 squared, and that gives us minus 7 meters per second. Next problem, part B. Using the same position function, now we determine the particle's average acceleration between 2 seconds and 3 seconds and the instantaneous value at 3 seconds. Okay, well, we have to obtain first the function of the acceleration in terms of time, and to do this we take the first derivative that gives us of the position function, that gives us 2 plus 6t minus 2t minus 3t squared. But then we to get the instantaneous, let's go ahead and take a derivative, a second derivative of the position function, giving us 6 minus 6t. Now, to get the average acceleration, we have to, using the definition for average acceleration, we take the change in the velocity of the particle over the time period that is stated. Well, that means we have to determine v at t equals 3 seconds, subtract v at t equals 2 seconds, and then divide by 3 seconds minus 2 seconds, which is 1 second. Okay, well, let's see. Since we have our velocity function, when we put the velocity at t equals 3 seconds, we get a value of minus 7. At t equals 2 seconds, we get a value of minus 2, and of course that is in meters per second. Divide that by 1 second, and that gives us a value of minus 9 meters per second squared. Using the instantaneous value for time 3 seconds, we determine that A at 3 seconds, the acceleration at t equals 3 seconds is minus 12 meters per second squared. And that's, of course, making use of the functional form which we obtained from the derivative. Next problem. A particle moves along the x-axis according to the equation x equals 24t minus 2t cubed, where x is in meters and t is in seconds. The question is, what is the magnitude of the particle's acceleration at the instant when its velocity is 0? Well, the hint here is get the velocity function and the acceleration function and determine the value of t when the velocity is equal to 0. Take that value of t and plug it into A. Okay, so v as a function of t will be given by 24 minus 6t squared. A as a function of t will be given by minus 12t. Now, let's take the value of v that we obtained, set that equal to 0, and we determine that t will be equal to plus or minus 2 seconds. Of course, we reject the negative value since that makes no sense. And so now that we've determined that the velocity is 0 at t equals 2 seconds, we make the substitution here and determine that the acceleration is minus 24 meters per second squared. Next problem. Here we're asked to determine the instantaneous value of the velocity of the particle at t equals 1 second. And what we see here in this graph is that we have some segments where the for which the velocity is constant over those segments from t equals 0 to 2, from t equals 2 to 4, from t equals 4 to 5, from t equals 5 to 7, and from t equals 7 to 8. Now, we're only asked to determine the value of velocity at t equals 1 second. We know that because the velocity is constant and given by the slope of the line, it doesn't matter what time is given to us provided it falls within t equals 0 and t equals 2 seconds. We proceed to obtain the slope of this line given as delta x, the change in the rise, over the run, delta t, and using the endpoints 10 minus 0 divided by 2 minus 0, this is of course in meters and this is of course in seconds, we obtain the velocity of this particle as 5 meters per second, and it's constant throughout this entire time frame. And we can proceed if we were asked to determine the velocity between t equals 2 seconds and 4 seconds in the same way, take the velocity of this graph, of this line. Now, the question is, would we get a positive value or would we get a negative value? Think about it. What about the velocity of the particle at between the time period 4 seconds and 5 seconds? Think about that. And then next, the between 5 and 7 seconds and between 7 and 8 seconds. Okay, here again we're given another graph, and from this graph we are told to determine the particle's speed at t equals 10 seconds and at t equals 15 seconds. Further, we're told that the particle starts from rest. And that is important because we know that our v initial when t is equal to 0 is 0. So let's begin by examining the graph that is given at the time period 0 to 10 seconds. We see that the acceleration of the particle is constant and equal to positive 2 meters per second squared. Further, we note that the acceleration of the particle from t equals 10 seconds to t equals 15 seconds is constant and equal to 0. So let's proceed. Well, we want to determine the velocity of the particle at t equals 10 seconds. Well, here we use the kinematic equations of motion with the equation final velocity equals initial velocity plus a times t, because a, the acceleration, is constant in that time period. And what we find is that at t equals 10 seconds, let's see, our v initial was equal to 0, a was equal to positive 2 meters per second squared, and so we find that uh, our v final is 20 meters per second. Further, we also know that between t equals 10 seconds up to t equals 15 seconds, the acceleration is 0. And if the acceleration is 0, then the velocity must be a constant also equal to 20 meters per second. It is only after t equals 15 seconds, in other words, between the time interval of t equals 15 seconds to t equals 20 seconds, where the acceleration takes on a value of minus 3 meters per second squared. And so if we were asked to determine the final velocity at t equals 20 seconds, now our v initial is equal to 20 meters per second minus or plus a negative acceleration, so minus 3 meters per second squared, and the time period would be 5 seconds, right, from t equals 15 to t equals 20, so 5 seconds, and so that you can see that the final velocity here would be 5 meters per second. Next problem. Let's take a break and begin with problem 6 in part 2. See you soon.